this new seminar. Today we have, the speaker of today is Federica Caforio. She is a postdoc at the University of Graz, and today's talk is entitled Development and Personalization of Multiphysics, Multiscale Models of Cardiovascular Function. So the stage is yours, Federica.
So first of all, good afternoon, everyone. And I would like to thank mostly Nicole and Guglielmo for inviting me and all of you for being present. I'm really happy to share my last results and interest in research with you. And I would directly go to the main context or main motivation of my research. I started thinking into this world of modeling for cardiovascular applications during my master's, so almost 9 years ago. And I could see in this decade that the interest and advances in cardiovascular modeling, both from the mathematical community and from the clinical community, are really growing. This is from, let's say, from the mathematical point of view, the beauty and the challenge behind it is the very complex interplay of physics happening at different scales, both in space and time, that are the basis of our cardiovascular function. And once the equations are done, are found or delivered, then still we have to discretize them, and we have to get then efficient softwares that are still stable and reliable. And this is just to get a heart or one heartbeat of a general patient. That is still very important in order to have information on some physiological or pathological conditions. But if we really want to then target optimized treatments or specific diagnosis, then we need to move towards the framework of digital twinning, and so integrate the data that we can get from the clinics to have to personalize such models. So I don't know if all of you are familiar with how our heart and blood flow function. I just would like to give you a short spoiler on that. And I've mentioned it's really an interplay of three main different physics. The first one is the electrical propagation, so electrophysiology. We have from our natural pacemaker spontaneous evolution propagation of electrical signals that then triggers a cascade of chemical reactions, and through the rise in calcium concentration, then the contraction at the level of the cardiac fibers that are called myofibers is triggered, then enabling the contraction of the chambers. These contractions and then this pump function that then is able to deliver the blood from hemodynamics through the whole body. And we cannot consider these three physics as silos, but as you can imagine, they're really intertwined, because the electrical signal is triggering the mechanics, but we also have a feedback from the level of stretching of each cardiac fiber that then is influencing the electrical signal again. And this all happens at the cell level, at really the microscopical level. On the other point of view, we have not only at the level of the heart chambers or at the valves, but also at the level of all the vessels, a fluid structure interaction. So a strong interaction between the vessel walls or the walls of the heart and the fluid. Then we have to consider the whole body, so the whole cardiac system, arterial, venous system, arterioles, capillaries. We have to consider valves and how to model valve, which level of accuracy. And the heart itself is made of cells, so needs nutrients, needs oxygen. So we have to consider perfusion models. I decided to structure this talk in two parts. The first one will be mostly dealing with forward modeling, and the second one, inverse problems. And I could not give you a whole overview of cardiovascular models, because that would need a lecture series, and maybe also would not be the most adept person to do that. I will just focus on some recent contributions that I made in this topic. And as I've mentioned before, we have to deal with all the vascular system and its effect on the heart function. How to do that? Of course, we could not rely on three-dimensional, very accurate, discrete representation of the system because of computational costs, because of then number of parameters, geometrical and physical, that we will have to personalize. We can rely on the other side on reduced order models, because they have a simplified representation, and so they deliver at a reduced computational cost important result or important impact on the cardiac function. And I dig a little bit in the literature, and what I saw was that actually, if you have a very accurate three-dimensional representation of multiphysics model of the heart, then the rest of the vascular system is lumped into so-called 0D models, or also called Wincastle models. To have a grasp of what does it mean, you can consider an electrical analog. Instead of having current that is traveling, then we have blood flow. And this blood flow encounters some resistance associated with the length of the vessel, the thickness of the vessel wall, their stiffness. There is a compliance, a capacitance associated with the compliance of these vessels. There can be inertial terms, and really we can make this perfect analog so that we can have then use Ohm's law or Kirchhoff's law to model that. On the other hand, there has been a big literature on developing one-dimensional models, so still reduced order model, but with higher level of refinement, and also able to take into account wave propagation. But these had maybe a high level of detail in the geometry of the vessels, but from the cardiac point of view, it was just lump model, like varying elastance model, or just flow or pressure profiles. So I tried to combine these two words. And so the governing equations are basically, for the cardiac model, electrophysiology, which is a reaction, modified reaction equational equation, where first of all, with the equational equation, we get the arrival time of the wavefront, and then we plug it into a monodomain equation and with an ionic model so that we get the full detail of the electrophysiology. This is strongly coupled, because, as I said, the electrophysiology triggers the contraction. So this is then embedded or coupled with a solid mechanics model, so based on Cauchy equation of motion, where the stress tensor is, through an active stress approach, the sum of a passive term and active term. The cardiac model, or the cardiac tissue, is actually highly nonlinear, and we can make an hyperelastic assumption, so we can derive this from a strain energy function that has a volumetric term, isochoric term, and isotropic term, and anisotropic term. We then can sum it to an active stress component that depends on the contractility, that acts mostly along the fiber direction and the sheet direction. And then we couple it with one-dimensional blood flow equations that are based on Euler equations. So conservation of mass, continuity of momentum, closing condition, it is the tube law that is associated with the constitutive law of the vessels, viscoelastic. So we have an elastic component depending on the stiffness, and a viscous component. This is all embedded in our computational framework that is carved at the Meduni Graz. And the topic here is really how to couple these two physics. And so how to find the optimal, the new state of deformation of the cavity as a function of the pressure in the cavity itself. We could either have a naive approach, a partition approach, where we just prescribe it explicitly, but there are phases in the art cycle where we have a rise or decay in pressure at isovolumic, at a constant volume. In that case, we could have oscillations in pressure because we don't know the compliance properties of the cavity. On the other side, we could treat it as an unknown, so a monolithic approach, which means we need to add an additional equation. And this is the approach that is more stable, a little bit more computationally costly, of course, but much more robust. What is then the closing condition? Well, we can consider, for example, that the volume at each time step that exits the cavity is the same volume that enters in the tube, let's say in the aorta from the left ventricle. And so we get the saddle point problem in two variables, U and P. After Galerkin discretization in Newton's method, then we get a block system to solve in U and P, and you can see some terms actually only depend on the three-dimensional cardiac model or on the 1D model. And then on the in the isovolumic phases, we can just say that the volume stays constant. Okay, so just some results. Here I considered only left ventricle model, patient-specific, and one tube that is like aortic segment, and then a simple three-dimensional Wien-Kessel model, 0D model. And you can see I consider also an empirical cenotic model. What we can see is that if we augment the stiffness of the vessel, as we can see here in the titles of these pictures, then we have a different pressure profile, both for left ventricle and for the aorta. Why? Well, that's because 1D models can take into account wave propagation and disruption. If we have higher stiffness, then the wave will travel faster. This wave is actually the sum of a forward traveling wave and backward traveling wave, because at each bifurcation in the tree, we get reflection of waves. So if the backward traveling wave is coming earlier, then it sums up earlier to the forward traveling wave, and also the decay is faster. So that's why we have higher peak and faster decay. And this notch here is called the necrotic notch. It's very physiological, and you cannot get it from 0D models because it's associated with wave reflections. What we can also see is that the higher the stiffness, the higher will be somehow the resistance to flow. So what we can see is that then the volume at the end of contraction, so-called endosteric volume, is lower if we have stiffer vessels. And you can see from here, the flow exiting the valve is also lower. But we can also see more complex arterial trees, like for example, this is composed by 116 vessels, and we have two different parameter set, one corresponding to a younger subject, one corresponding to an older subject. In the older subject, we have higher resistances, higher stiffnesses, and this results in a higher pressure profile. And you see this reflection arrives also earlier, so the decay is different, as in this case, corresponding to the younger subject. But also what is striking is that the flow exiting, so the volume in the left cavity at the end of contraction is much higher than in the younger subject. So the flow is much less than in the case of younger healthy subject. We can also track how these waves, so pressure waves and flow waves, are propagating in a branch, let's say in one arm, from more proximal to more distal places. And we can see this well-known physiological effect of pulse wave amplification, because as long as we go towards more distal locations, then we have bifurcations, and so the wave is reflected. So if you measure the pressure here, it will be much higher than the pressure measured at the left ventricle. And here we can see, of course, the flow then is split into the different branches. Okay, so to close up this first chapter, we propose this first coupled model that replicates the physiological behavior associated with pulse wave propagation. And there were also in the paper, we proposed different benchmarks to show the efficiency of robustness. And if you compare with the 3D 0D approach, actually the main cost is associated with the 3D model. So adding the 1D model does not increase the full computational cost. And this is very suitable in some clinical application where we need to take into account wave propagation and disruption, like hypertension, pulmonary hypertension, systemic hypertension, or aortic coarctations cases. And I've also been working on sensitivity analysis on the full electromechanical coupled model, but to perform it in a variance-based sensitivity analysis, I use surrogate models like GPs, and I have an article now under submission. So in more recent months, I've just finished supervising a master thesis on a closed loop model of hemodynamics, so 1D closed loop global model coupled with four-chamber model, and we're also extending the sensitivity analysis to such more complex models. Okay, let's now move to model personalization. So, as I've mentioned in the introduction, there is really a high need from the clinics to to have at their disposal personalized models that then are able to really meet specific criteria and of reliability, and they're validated, and they're able to then optimize treatment or better define diagnosis. To do so, we need to deal with the complexity of the models themselves and the availability of clinical measurements, which also come with error sources. So they are also affected by uncertainties. And in this, so there are a lot of challenges in this field. I recently contributed in two directions. The first one was the generation of a stress-free reference configuration at the same time with an automatic identification of constant stiffness properties of the chamber, and newer methods in scientific machine learning, again, to perform parameter estimation for heterogeneous field. So quickly on this first, so 2.1 section of my talk, we here first of all wanted to get a reference configuration at zero pressure. Why? Because you have to imagine from the imaging data, could be CT, MRI, let's say MRI for this moment, like scene MRI, we have information, geometrical information at different time steps. And we can have maybe our reference as end diastolic configuration, so at the end of relaxation. But at the end of relaxation, we still don't have a real reference configuration because there's still a pressure, end diastolic pressure. But in order to run our simulations, we need to have the reference configuration at zero pressure. What we can do is to have a backward displacement method. This is inspired by Cellier method. What do we do here? We start from our image data, and we know what the end diastolic pressure is. And what we can do is to inflate, actually. So we consider as initial guess that our initial image data or mesh is actually a mesh at zero pressure. So inflating up to P hat, we then have a difference, a nodal difference between the points between the mesh at our zero pressure and at the diastolic pressure. We can then subtract this nodal displacement, so this residual, and then we get to that point. We consider that this R1 is actually our new reference configuration, and we inflate again. We consider the residual, we subtract the residual, so the nodal displacement, and we get to R2. And you can see in this graphic, after 4 iterations, actually we get to our X star, so our real stress-free reference configuration, such that once we have inflated it up to end diastolic pressure, we get our image data. And what we also did in order to make the algorithm more stable, more robust, was first of all a line search that is damping actually in favorable directions. And in order to make it even more robust, we consider different magnitude, different scaling factors, such that, again, if we see that some direction is not really favorable for our algorithm, we then consider among all these scaling factors, what is the one giving the lowest residual, and maybe it's a very low scaling factor, so dampening this direction, and then we take that. So we saw that this fail-safe feature was actually highly improving the robustness and also the computational cost of the method. This is at the same time associated with an identification problem for the passive properties. As I've mentioned before, when I discussed the 3 main models, or the governing PDEs, I said we have hyperelastic formulation. What does it mean? We can actually say that our stress is strictly dependent on a strain energy function that has a volumetric term and an isochoric term. The volumetric term actually is based on a penalization of near incompressibility, because we know the soft tissue, the heart, is full of water, so it's nearly incompressible. What we can do to constrain that is to consider that J, that is the determinant of the deformation tensor, must be as close as possible to 1. So we have this quadratic term multiplied by a scaling factor called bulk modulus that is set very high. And we have an isochoric term This isochloric term is then a sum of nonlinear terms, usually exponential terms, that depend on A's and B associated with stiffness properties and nonlinearity. And you can see there is a term that is actually isotropic term along fiber direction, because as I've mentioned, the heart is made of fibers. So we can have a fiber direction. Actually, they are arranged in parallel sheets, so we can consider sheet direction and then a normal direction. It is normal to the thickness of the ventricle. So we have contributions in all these directions and in the mixed directions, so in the planes. And we want to fit the AIs, BIs, first of all, scaling all those by some alphas and betas, and how to scale them, how to personalize them based on the image that we have. Well, we can consider an empirical closed curve that is end-diastolic pressure-volume relationship. It's an exponential curve that explains the passive, so the constitutive law, the passive properties of the heart, by having just one pressure volume pair during the unloading procedure. So what do? We have our target, our ground truth, that is this normalized ADPVR from clots, and we fit it to our, so we fit these coefficients to the clots curve. We have then A fit clots and B fit clots with respect to the image that we have. And this is the model function that we fit with respect to the clots relation. Then we repeat the same fitting, but from the simulated PV curve during the unloading procedure to the clots curve. We get then A fit sim and B fit sim. Whereas this is a convex law, so both are positive, in this case, we could have some simulated PV curve that are locally concave, so this B is could be negative. That's why then when we compute such scaling that at convergence shall be as close as possible to 1, we can consider here the absolute value. So what do? Each time of the unloading procedure, actually, we update the material parameters, then we perform the passive inflation, we compute the nodal error that informs our backward displacement method with respect to our target configuration, and then if it hasn't converged yet, then we iterate. Otherwise, we have then at the same time the fitted final material parameter that are as close as possible to our ground truth clots relation and our reference configuration. So this is what we do after for some iterations, and both fitting are performed with Levenberg-Marquardt method. So let's see some goodness of fit with real data. These come from a data set of 19 cases, either with aortic coarctation or stenosis of the aortic valve. And you can see that if the dotted line is our target curve, a DPVR curve, so end-diastolic pressure volume relationship, then we have really a very well match. And this is our initial point, so PV pair, pressure volume pair, that is measured, and this is then what we get as volume at zero pressure. Also in this case, we have a very good match. Concerning computational time, what is interesting here is that during the unloading procedure, actually, we don't have to consider fully converging Newton, so we can consider just 2 Newton steps to have a decent, actually, reconstruction estimation of the unloading procedure. So actually, if you compare it with the validation phase, where there we have a full inflation case with fully converging Newton, actually, the pipeline is just 3 times slower. And the higher the number of elements in the computational mesh, the higher the computational time as expected. And we performed a really in-depth sensitivity analysis, considering, for example, different constitutive laws, because I haven't mentioned that yet, but if you're familiar with cardiac model, you will see there is a big portfolio, big dictionary of different models that you could consider with higher level of detail, maybe just considering fiber contribution or orthotropic, but only considering some terms and neglecting others, adding dispersion of the fibers. So you can really play with all these models. They all have different parameters, A's and I's. So we then wanted to see how well each model matches with, of course, different scaling factors, and actually the the algorithm is quite robust, so we have a very good match in both cases. We also consider sensitivity to, let's say, the uncertainty on the end diastolic pressure or on the end volume, end volume, end diastolic volume, or considering P1, P0 element for the model, or fully stabilized P1, P1 model. And we saw that the model was really, the algorithm was really robust with respect to that. So to wrap up this part, the algorithm is really very suitable to identify personalized passive material parameters and estimate the unloaded reference configuration. The pipeline is flexible to every finite element package and different constitutive models. And what is new is that we just need one pair of pressure volume at one time point and not two to fit the patient-specific EDPVR, along with one image data, for example, at diastole. Okay, then as promised to the organizers, I will also give more weight on parameter estimation in cardiac mechanical models. So I don't know if all of you are familiar with PINs, but let's say it's neural networks. So let's consider classical feed-forward neural networks. But here, we not only want to reconstruct a field, we also know if we want to perform inverse problems, that this field is parameterized by some parameters. So we know also that this field is covered by physics. So we know that it satisfies a differential equation, maybe with some boundary condition, if we have a time-dependent case with some initial conditions. And what is important to note here, maybe we are in this regime where we have some data, we have some knowledge of the physics, maybe with some uncertainty on the physics itself. So we want to get the best out of this information. And maybe the data that we get is also noisy. So in a schematic perspective, we have as inputs of our neural network spatial coordinates, we have time, and we get at the same time u, and with some just changes of lines, we also get the underlying parameters. Satisfying the PD, constraining the PD, we restrict the space of admissible solutions, and then we can get the optimal weights and biases of the neural network and the optimal parameters. So if we want to have a look at our cost function, it has two terms, the one coming from the data discrepancy on the data that we have, and the other one is a regularizer associated with physics. And we will see this is evaluated on some arbitrary points. How to evaluate the physics, how to compute the derivatives. What is really nice, what is a really big advantage of PINs is that actually we don't need discretization of the computational domain. We don't need what we do normally in scientific computing, finite difference, finite schemes, finite volumes, because our solution, our field is actually expression of neural networks. So it's a combination of nonlinear activation laws that, by the way, need to have some smoothness so that the functions adapt to consider second derivatives, so they need to be at least two, and affine functions. And so we are able to compute on the fly analytically all the derivatives that we need to compute to evaluate our PD and boundary conditions. So if we want to have a look on the different losses, we have the data discrepancy on the observation points. We have residual of the PD on arbitrary points in the volume that we can decide how many and where to put them, and boundary condition, maybe also initial condition, residual, and then we can add our regularizer like weight decay. And just have a look, we have here weights, so other upper parameters that not only take into account the adimensionalization of such losses, but also compensate or are responsible for the specific weight of each loss. And I can tell you, since I had already a couple of years of experience on this topic and also from the literature, it's not necessarily a naive problem to define such heavy parameters, but there are methods to automatize that. what we consider, so what is our contribution with respect to the vanilla approach is that, first of all, based on a continuation approach, we divided the training into 2 steps. So starting from the random initialization with Glorieux, Xavier-Glorieux initialization of weights and biases, first we do a pre-training considering only the loss term on the observation, and then we get a nice initial guess that we use to do the full loss, so to do the full training. Also, each of these steps is actually based on a 2-step optimization. First of all, with the first order ADAM optimizer, and then we speed up the convergence with the FGS optimizer. Again, so that we have a speed up in the cost, but also on the other side, we don't perform the FGS from scratch. That would be more more sensitive to local minima. The data that we observe is noisy. In clinical images also they get noisy. We can consider for high signal to noise ratio, consider, for example, MRI, that this noise is white Gaussian with STD or variance that we can set. And you will see this LD coefficient, level of dispersion, that we defined as 3 sigma divided by the maximum displacement. Okay. But what happens if the parameter is not a constant, but it's space dependent? Well, what we can do is that it's a field, we just model it as a second neural network. So we will have at the same time 2 neural networks to simultaneously train based on the same losses that I have described before. And maybe we can add some prior knowledge on the range where this parameter, physiological or pathological, it can live. And so if we want to see some first results, let's start with the passive stress and quasi-static model. We have here a static, so a quasi-static Cauchy equation of motion, just divergence of a stress tensor, a first hierarchy of stress tensor equal to 0. This is our computational domain. Let's consider it as a slab of the myocardium. We have pressure, Neumann boundary condition at the 4 sides, and on the upper and lower face, spring-like Robin boundary condition. Again, our stress can be derived from a strain energy function. In this case, we consider, just to simplify things, isotropic Neo-Hook law plus a volumetric term where we constrain, where we penalize annealing compressibility. But the complexity here is given by mu. Mu, the stiffness appearing here, is not a constant, but it's space heterogeneous because we have a scar. So we have an area, a spherical region, and actually we also have some gray zones, so some surrounding regions where the stiffness is higher than the alpha case, but not as high as in the scar. And so we have to try to estimate where the scar is located and how the properties, the stiffness properties, have changed there. And we can also make the work even less easy for the pin, because we can say, well, but actually in the MRI, you don't have the same resolution as what you would have using your in silico solution to get the data. You have pixelized data, so we also consider that. So lower resolution of the data and averaged in every pixel, in every voxel. And actually what you can see is that, again with noise and again with lower resolution, just having information on the displacement and strain, that is something we could get routinely from MRI imaging, we have a very good estimation, like lower than 5%, and also a very good reconstruction of the displacement field. What is also very important from a clinical point of view is that not only we're able to reconstruct very well the displacement field, but being totally blind to the stiffness properties, just seeing this data non-invasively, we can say where the scar is and how higher the stiffness is. What you can also see is that this solution, the ground truth solution, is constant by part, and the pin tends to smooth out. We know this is called the spectral bias. This is a very well-known limitation of pin. I have to say we have also worked with adding, so considering Fourier features, so adding a non-trainable layer where instead of the spatial coordinates, you rewrite everything in terms of cosinus and sinuses of a b times your spatial coordinates, where b is taken from normal distribution, and you can play with sigma of this normal distribution so that you can take into account higher frequencies. In these test cases, we did not see a huge difference, but we are analyzing that further. What is also very important is that we can get a very good match in secondary variables, like strains, where I have to say in this case, we also have some information, but we did not have any information on the stress. Since the stress is obtained by enforcing the PDE, we're able to have also a good idea of what the stress tensor, how the stress tensor looks like. So this is really important because it's also a very important informative clinical data that we could give to the clinicians. Okay, let's now consider fibers. Here I have a transverse isotropic load. It's called Buccione law, and mu is the stiffness parameter that we want to estimate here. We consider all other parameters as given, but we consider two different test cases where either the fiber orientation is constant or it varies along the normal, along this thickness of the slab. And so you can see the in silico solution looks different. Also, in this case, we have a very robust estimation of the stiffness. In this case, the stiffness is a constant, and also in the case of varying fiber orientation. Again, we can say, well, you're maybe cheating because you know what the model, the underlying model that you use for the ground truth data is. What happens if you just have images, you don't really know, as I've shown before, there are different models, you don't know which one fits your data best. So why not considering a mismatch between the data that we have, so the underlying model of the data, and our hypothesis in the pin. That's exactly the objective of this test case, of this benchmark. We consider one fiber Rozaffe logden for the data that we generate in silico with our CARP in-house code, but we train the pin with another law that, as you can see, delivers the same displacement field. If you superpose them, well, I cannot really see a big difference. And so what we can see in this case, and I found it really interesting, is that not only we have still not such a bad estimation of the parameter mu equivalent, even though it's we have considered a different model, but also adding noise seems to have a regularizing effect. So it seems that, as we have seen, as you can see in other contexts of machine learning, adding noise sometimes makes your prediction more accurate and more robust. And in any case, the reconstruction of the displacement is really good because it was the displacement delivered by the two models was really very similar. Okay, let's add contractility. Here in this test case, we have our active stress approach. So we add contractility. We're still in quasi-static case. We have here a cube instead of a rectangular slab. This phase, in this phase, we have homogeneous Dirichlet. Everywhere else, we have homogeneous Neumann. The model, the passive constitutive law is transverse isotropic, the Buccione model. Here we give mu and k as given. What we don't know is this SA, that is a contractility that acts mostly along the fiber direction. What we know as a ground truth is that for this test case, SA was equal to 118 kilopascal. And again, here we just consider displacement information, and we have a very good match. So the relative error is roughly 1%. But also I wanted to show this graph because you can see we have a very low generalization error. So the discrepancy between test and train error is really low. Also, I didn't mention before, but you can see this two-step convergence because this is the Adam phase, and then you can see really this gaining convergence using the FGS. Also, here I think you can appreciate much more than the other cases So that's why I would like to enhance that. You have a solid line and some shaded area, because we wanted to see how robust our prediction is considering different initialization of weights and biases. So we consider different seeds for this initialization. And so the solid line is the mean, and then the area spanned by the trajectories is the shaded area. Okay, again, you could say, well, but MRI is not a volumetric information. You have slices, you have stacks. So what you consider is that we have slice structure also for the data point, but also in this case, the prediction is really robust with respect to that, and with respect to noise, we have 1% without noise and roughly 6% with noise. We can also consider fiber variations. So here we have this transverse isotropic model, but with fibers varying along the Z direction. And here we can see, again, we have a very good error, a relative error on SA. So it is robust also in considering more complex constitutive laws. And what about fields? What about having a heterogeneous contractility? Because again, if you have a scar, not only you will see that the tissue is more fibrotic, so it won't inflate, it won't deform very much during relaxation. But also during contraction, the cells are almost dead, so they won't be able to contract as well as the healthy cells. So we're gonna see a rapid decrease in contractility. And again, here we consider a gray zone where the contractility properties are like halfway between the healthy and scar tissue. So the PIN solution, again, with this spectral bias, so it's a smoothened version of the ground truth, but is matching very well in terms of qualitatively and quantitatively the properties, the scar. If we apply a binary mask where the threshold is the average of the healthy and pathological contractility, well, we can see that actually the solution of PIN is slightly maybe overestimating some area, slightly underestimating some area, but we can say there is a very good match. And what about having two scars that are really close to each other? Is the PIN able to detect that there are two scars and not just one big region? Well, we also could see that taking different slices, we can see very well that the PIN is able to detect that there are two different regions with a very good match with respect to the ground truth. Okay, last example, it's a time-dependent model, because I've been speaking about beating hearts, but until now you just saw frozen hearts. And what about the beating heart? We can consider here the time-dependent Cauchy equation of motion. The passive stiffness constitutive law is, so the passive constitutive law is the same. The active term is now depending on a scalar SA that is not anymore a constant, but it's time dependent. It is actually, so this is the in silico data that we developed, that we defined. And SA is solution to an ODE that is called Bestel-Clemenceau-Ring ODE. And what is nice to see is that the maximum contractility that is attained at the peak systole is actually scaling the full profile. So the higher or the lower the sigma zero, the higher or lower this peak. But actually, if you consider the function itself, it's the same, it's just proportionally scaled. So in the PIN, we don't have to add the solution, the solving of an ODE. We can just rescale the solution to an ODE by this sigma zero. And what we can see here, we had its data slices of displacement and strain. What we can see here is that actually the solution of the PIN is reconstructing really well the ground truth displacement. So the error is really low, but also the hidden sigma zero, it is a constant, homogeneous in space, so constant in space, is captured, is learned very well, also in presence of noise. So just to conclude this part, we developed a very efficient and versatile algorithm, and its robustness convergence property, again, were proved in different benchmarks. I was able to have a different, mostly one master student, actually, now two, on this topic. And we are working on estimating active stress properties and scar detection on now also on more realistic geometries. And for that, I'm also considering advanced methods to reconstruct high resolution displacement fields from MRI data. We're also working on more robust or more theoretically sound inverse uncertainty quantification, considering everything in the Bayesian framework and not just ensemble pin, considering different initializations. With my master student, Matthias Hofler, we're also working on finding generalization error of pins for inverse problems with nonlinear PDs. There are some results for forward problems or for linear PDs. We're now trying to get this upgrade of complexity. And my end goal and dream would be to apply this to a clinical setting. So I would like, first of all, to acknowledge funding schemes. I got last year a grant from L'Oréal UNESCO, Austria. And now last June, I got a bigger project of 100,000 euros from the region of Styria, where Graz is located, to hire master students to work on the project. And last but not least, I would like to acknowledge all my collaborators. Without them, I could not present so many results. First of all, from the Department of Mathematics and Scientific Computing, Professor Hase, who is my supervisor, and my colleagues, postdoc Elias Carabeles and Thomas Granditz, and my master student, Matthias Hofler. Our collaborators from the Medical University of Graz are Professor Planck and Professor Augustin, and postdocs and research scientists Anton Prassel, Alexander Jung, and Matthias Xell. The 3D, 1D forward modeling part was in collaboration with Dr. Jordi Alastri from King's College. And the PIMS project is a collaborative project with Professor Alfio Quarteroni, Francesco Regazzoni, and Stefano Pagani from the Department of Mathematics of Politecnico di Milano. And now, thank you for your attention. I'm really happy to take questions if you have.
Thank you for your interesting talk. Modernistically speaking, is really high level, I would say. So,
thank you. That's why it's a collaborative thing. So I think working with such multiphysics, multiscales model needs a higher, so a number of different competencies altogether. Otherwise, it's really difficult to make advances. And I mean, we know also there is a big expertise in this specific application case, the Politecnico di Milano. You really need a group synergy to achieve those.
Yes, yes. Yes. Any curiosity, question? Also from online?
Hi, thank you very much for the wonderful talk. And I'm looking forward to this talk. Actually, I'm wondering about a bit on cine MRI, which you have mentioned. So I'm wondering whether the cine MRI you have tried to improve the flow field data or try to improve the whatever the DICOM data, or maybe we can say some kind. Sorry, not DICOM, but the imaging data. So I'm not sure what if I'm getting the correct, because what I understand.
Thank you for your question. From the cine MRI, actually, we're not interested in the flow. We're mostly interested in the displacement. So the idea is that having a cine MRI, hopefully at really high resolution, let's say short axis or long axis views, you can track points, material points. And there are now either methods like feature selection, or there is now a more recent method, it's called warp pin. That is actually something I'm now really like I've started 1 month ago to investigate with another master student of mine, where you can get higher resolution displacement and strain fields, because otherwise from the CNMRI alone, you could only trigger or try to follow points on the contours like epicardial and endocardial contours. But the idea, I haven't really mentioned that, but the idea is that I would like to detect scars, not invasively. Usually the gold standard is to use LG MRI. I don't know if you're familiar with that. It's called late gadolinium enhanced MRI. You get a contrast agent, and then you see how this agent is absorbed and washed out by the tissue. And if you have a scar, so if you have a dead tissue, it won't be washed out. So if you then image it, you will see this stain. The problem of this contrast agent is that you cannot give it to people with kidney problems or with diabetes. And there is been now a recent evidence that it actually is not totally washed out from the tissue. So at the long term, it could be not totally unharmful for healthy patients. Also, it is extremely expensive, and not all the hospitals have it. So my idea would be to have a cheap version, because CNMRI is much more diffused in hospitals, much less expensive and less harmful. So the idea is really considered solid displacement, not flow.
Okay.
I hope I answered.
Yeah, thank you very much, because I started to work on CineMRI to extract the model, but it was like the image was not good. But now, thank you. I will look into the paper more. Thank you so much.
Thank you.
Federica, thanks for the talk. So I have just a naive curiosity. I was wondering whether you have a heuristic for switching between the Adams and the BFGS optimizer, or any rule you may suggest.
You use the very perfect term, that is heuristic, because we did not find actually, oh, sorry, I was going in the wrong way. Let me see. Well, maybe, let's see if I can find a nicer. Let's say this, for example. So what we saw really heuristically was that if we start the BFGS part, BFGS, sorry, so that you see it better. If we start the BFGS optimizer, when this curve is then starting to decay, because at the beginning, actually, you could have a very nonlinear or non-logical learning procedure of the ADAM. But if you start the BFGS when the ADAM is already, let's say, converging to a minimum, then it works really well. There are sometimes some phases, especially with more complex laws, where the ADAM is first going down and then going up. And then again, you should maybe wait that the ADAM, so the gradient of the ADAM is again in the good direction, so that then BFGS is really working properly. If you do the BFGS too early, then we saw sometimes it just crashes, in the sense that the BFGS gets stuck into a local minimum, and then we cannot really the simulation then stops. But again, we did not really found a formula or a rule. It was just saying for that data set how the ADAM when we could see, okay, this is now in a good phase.
Okay, thank you very much.
Thank you.
You're welcome.
So, Federica.
Hello.
Thank you very much for your talk. Actually, I wanted to ask you a question about why did you choose BDF, BDFG algorithm for the optimization? I mean, could you choose something better? Because in the end, you have a least square problem, and you can use some Gauss-Newton, which usually converges much faster than BFGS.
Well, in terms of convergence, we saw that BFGS and like the LBFGS, it is limit memory BFGS, works really well. I also have to say, other methods like Gauss-Newton, I haven't really saw them applied to neural networks, but it's maybe my limited experience on that. And usually the vanilla, let's say the vanilla approach, the vanilla pin, is only based on Adam. So then you can see usually like 300K epochs usually for 2D cases, and it's not nonlinear mechanics, it's like, let's say, reaction diffusion, or maximum you could see like Allen-Kahn equation, but really very simple framework. And then they need a lot of iterations. We saw with BFGS actually, and especially with this combination, a good trade-off between accuracy and number of iterations. But we haven't tried, actually, I have to say, with other options. We found this because it's second-order convergent. That's quite good.
Okay, I can also say about like the change between Adam and BFGS. Okay, maybe you would like to look in the Lovenberg-Marquardt algorithm, which is basically like has the idea behind that it automatically change between global converging first order optimizer and locally convergent second order optimizer. So it's
yeah, of course, that would be a nice idea. So to automatize, you mean to automatize the switch?
Yes.
Yes, absolutely. We haven't really thought about it yet, because still we're not. We still saw that there is not like a huge difference in number of epochs from Adam and then epochs from BHFs. They're usually between 600 and 1,000, and we really didn't see a huge difference between different test cases. In our experience, and now with my master students, we're really working in depth on that, also analyzing Pareto fronts. It's the main trigger or the main aspect to take into account that I quickly mentioned in the seminar is not even the number of collocation points that you could consider, but also because all the losses are normalized and adimensionalized. It's the weights. So actually, the main thing that you have to consider properly, and again, you could do some manual tuning of these hyperparameters. You could do a random search, a grid search. We consider adaptive biases. We consider a novel approach by Kaniadakis and colleagues. It is called residual-based attention mechanism. This is really what is influencing mostly your convergence. And for the Adam to BFGS, we set it once for mechanics, and we're not really modifying that well. So that's why we did not really think. Of course, it could maybe improve, but we saw the main impact was not 100 iterations more of epochs, but rather defining what is the good combination, the good ratio between so data against PD.
So that's my next question. So okay, you mentioned that you use data sets, and like what is actually the main case? Like how these parameters are distributed between themselves? Which like.
Sorry, I didn't get the question. Can you maybe get closer? Sorry.
You mentioned that you try to use the Pareto sets in order to choose the parameters, how to balance the functionals inside the pin. And from your experience, which part of the pin is actually the most, has the highest weight?
You mean based on the Pareto front analysis?
Yes.
What we are now seeing is that, again, it's quite independent, or to a certain threshold independent from the number of collocation points, but it seems that actually this pin framework is really best suited when you have some data and some physics, and actually in these cases in mechanics, the physics shall come as a regularizer, but the most weight shall come from the data. So we saw that like with the 60 to 30%, or like, I mean, if you divide by 3, then maybe 60% and the rest is between PD and BC is the best contribution, or at least the highest, the majority of the weight of plus 50% shall be in the observation. We still are investigating if this is maybe due to the fact that we have the in silico data that is still the PD, but then discretized. So it's a finite element representation, discretization of the PD. So we have to take into account the approximation in terms of a model uncertainty. So the data that we have satisfies the PD, but not really properly, like point to point. Is more a residual that is really low. Maybe it's that one. Maybe there are other aspects that affect this optimal choice that is mostly towards observation rather than PD. We're still investigating that. But also if we can consider that we have the data, and again, as I did in the experiment with this uncertainty of the model, we have clinical data and we cannot really say what is exactly the PD satisfied by the data. We know that they satisfy some physics. So I think it's good that we have mostly the data, knowing that they're noisy, and adding a small contribution from the PD and boundary. But we're still analyzing it. So this is our, let's say, theory. Now we're trying to further prove it.
Amazing. Thank you.
Thank you for your questions.
Okay, let's thank again Federica.
Thank you again for your attention.
Okay. Nisha?